All right. All right. Does anybody have any comments on the talk yesterday? I noticed that he brought in some cosmology issues. He talked about Dirac and some of the other things. And I was just curious, does anybody have any comments about that or questions?
Yeah, he brought in this very large number business. I
Yeah.
think people have thought that it was rather scattered. In fact, I think he even sent me a note, by the way, just after the lecture, saying he thought he could maybe improve upon the presentation at maybe a later stage. But there was a lot of material there, but it was a bit scattered, I thought, very hard to focus on.
Yeah, that's why I suggested you probably need a kind of a flow chart of how the ideas are connected together, because it seemed like he jumped from one set of and suddenly was talking about something else, and that was kind of confusing. Needed a flow chart, I thought. All right.
I agree with you.
Excuse me.
I absolutely agree with you. It was scattering, no ideas. I misunderstood what he wants to show, to tell us, Too much equations, too much something, and everything around, but any logic in his lecture.
And perhaps at the end of the day, we were none the wiser about the difference or similarities between mass and charge, which was meant to be what his lecture was about, but he dealt with maybe scores of other things.
Yeah, and it was based off an ether theory also, which I don't.
Yes, but ether theory, it doesn't. I don't know. Let me tell you, I don't know. I don't know what does it mass of particles. There is no mass. What is the charge? This is the most critical, question about. I suppose maybe he will give some definition what he means by charge. And the very last moment, don't use classical notions in quantum physics. Many times I told the same. That's why transfer our knowledge in classical physics to quantum physics, it's not fair. Sorry.
All right, I prepared a little presentation. Roger's not going to be talking next Saturday, and he passed it on to me, and so I'm going to be talking next Saturday. And my kind of thought was to sort of combine some of these short presentations that I've already talked about into a presentation Saturday. And so one of the things is that I talked about dark matter a little bit last week. And so now I'm going to talk a little bit about dark energy. And this is an example of the terminology. You have to sort of get beyond the terminology confusion. Does this concept even have any real meaning? It's kind of an issue that you get to in the beginning. Anyway, this guy, Tim Radford, has this interesting quote, and he says, now he's talking about cosmology in general. He says, in a nutshell, the universe is 4% visible, 23% undetectable, and 73% unimaginable. Welcome to the cosmos, full of mass you can measure but not manhandle, driven by a force you can infer but not explain. And this comes from I think he sort of, in a way, sort of sums up the issue about modern cosmology. He's being kind of, I would say, a little bit facetious. And now we're back to this David Merritt, that Wikipedia mentions. At the end of the dark matter article, they mention David Merritt says, astrophysicist David Merritt identifies dark energy as an example of an auxiliary hypothesis, an ad hoc postulate that is added to a theory in response to observations that falsify it. He argues that the dark energy hypothesis is a conventionalist hypothesis, that is, a a hypothesis that adds no empirical content and hence is unfalsifiable in the sense defined by Karl Popper. That comes from Wikipedia, and I'm not really sure why they add that in there, and then they say, well, the majority of physicists don't believe this, so we can ignore this criticism, which I think I think that's kind of ridiculous for them to ignore a criticism that looks like it's to be right on. Okay, so at the NASA site, this woman wrote an article about what is dark energy, and this is at the NASA site, so that gives it kind of a orthodox blessing, you would think, that this comes from the NASA site. And it says 9 billion years after the universe began its expansion, it started to speed up, driven by an unknown force that scientists have named dark energy. Okay, key point. It doesn't start happening until 9 billion years after T0, or the moment the universe begins. So 9 billion years. Now, some people say 5 billion years. That's kind of a point of confusion there. But what exactly is dark energy? The short answer is we don't know. So this is another hypothetical, we don't know, but we think it exists because we need it to fix our models. It's making the universe expand at an accelerating rate, and approximately 66.3 to 70% of the universe is dark energy. I have no idea what they mean by saying that. What do they mean by, how can you say 70% of the universe is dark energy? What does that mean? Are they converting energy into a matter equivalent? I was never able to really figure out exactly what that meant. So that's something maybe somebody can answer if they know. Right now, dark energy is just the same that astronomers gave to the mysterious something that is causing the universe to expand. Okay, so dark energy is just a name that they give to the fact that the universe is expanding. And what accelerating? What is this? What are they talking about? That's kind of first thing. More from the NASA site, the term dark energy. Okay, so the term dark energy is sort of, well, we sold people on the idea that there's dark matter, so now let's sell them on the idea that there's another mysterious thing called dark energy. And so this guy, Michael Turner, supposedly coined this term. He wrote an article in 1998 where they looked at, there are two projects that we're doing, the supernova, type 1A supernova, and plotting them on the chart, and came to the conclusion the universe was expanding and that 2/3 of the critical energy density, I'm not sure what they mean by that, exists in a dark energy component with negative pressure. I don't know what negative pressure means. And so here I say, okay, it's kind of ambiguous. What they mean is that the universal rate of expansion is increasing. So the rate of expansion is increasing. That's what they mean. It's not exact. Some of the descriptions that you find, that's my experience, is kind of unclear. Okay, why is it called dark energy? Okay, this guy Turner, I'm not really sure I believe what he says here, but anyway, he says the name was extremely intentional. Well, he intentionally coined this term. When the evidence first began to appear for dark energy, he said, many scientists figured it was a simple problem that would be easily explained away. He didn't want that to happen. I wanted a name that would say, this is a really big mystery. Don't jump to conclusions, and I think it worked. So this looks to me like scientists are trying to deliberately create an unsolvable mystery. And I think it's kind of disingenuous for him to, it's probably he was looking for attention more than a solution. Okay, so here's a drawing that shows, and you see this drawing a lot. I'm not sure it's really, this is kind of a, space is treated in 2 dimensions. Time is in the horizontal axis. Space time is on the vertical axis, so it's going towards the top. Starting from the bottom, time is going from the bottom to the top. And this is a 2-dimensional section of space. And what they mean to say that it's expanding is that the top part is, it's kind of an exponential function. Okay, and that's really a key description of it. It's exponentially increasing. So space is exponentially increasing, which means that it's not going at a linear, it's not a linear expansion. Space is not expanding literally, it's expanding exponentially, which means that it's increasing. Okay, so here's an example of the measured data. Vladimir says, well, we have to have experiments. Astronomers don't do experiments, they do observations of things, because they can't do experiments. This is a chart of the data, and the data is above the green line, which I believe to mean that that's the projected, what they're looking for. It's above the green line, so the universe is the universe is expanding faster than they thought. Here it is here. Now, then they use this term, the line with the red dots is with dark energy, the dashed blue line is without dark energy, and that's basically their that's their observational evidence.
Does that boil down to like observations of the redshift? How is that determined that the universe accelerates?
Well, that's a little bit complicated. You'll get different. It's distance scale versus redshift. On here, this chart here, it's distance versus redshift. Okay, and redshift is on the bottom, and brightness is on the left-hand side. I'm not sure what they mean by distance. This is another issue that I have with these charts that they put out. They don't really have uniform. There's different scales and different ways of doing it. The idea is that there's a projected, what they project for their universe, and a constant expanding universe, and the data indicates that the universe is expanding faster than their projected model. Does that make sense to you?
Pay attention how many points of measurement they have. And these are very important. 70% of energy on a few spots of measurements. Unbelievable.
Well, they've got not very many points out here at the at where it really counts, and so then they do curve fitting, and it's a lot of. One of the problems I have is, and if you really want to get into the details of it, in this particular chart like this, which is supposed to be a plot of measured data, it's corrected. These measurements are corrected by corrections. They apply corrections. And then the question becomes, what's the basis of these corrections that you're using? They're corrected by assumptions about the absorbing matter in the galaxy, our galaxy, the Milky Way. And there's other corrections that go into plotting these data points. So this gets you into, I'm not really sure what they're plotting. That's, to me, that's really where you're getting into technical, really pretty technical aspects of it.
There's a departure of experiment from the contention that there's a linear relationship between redshift and distance. That simple linear relationship is falsified, if you like, by the experiment. Now, the problem is that they've interpreted redshift as being due to Doppler effects, and therefore, in order to save that theory, they have to introduce this business of acceleration and dark energy. But
Yeah,
I would say that the theory is wrong from the get-go.
Yeah, you could. Yeah. I'm going to talk a little bit more about that. All this stuff is kind of murky, and they don't really. To me, I think it's it has this appearance of ad hoc. There's a lot of ad hocness to it, but they don't really. They like to present it in a way so that you can't question that it's ad hoc, or you don't see the ad hocness of it. And anyway, I'm gonna the thing at the first thing that starts to get confusing is when they start identifying the cosmological constant with dark energy. Okay, so here the question is, why is dark energy needed if the cosmological constant exists as an equivalent concept? So why don't you just call it cosmological constant energy or something like that? But they don't do that. They've invented this new term when there's a term that already exists. This is kind of confusing. And the cosmological constant is supposed to represent the repulsive force that opposes gravity. Okay, so this dark energy opposes gravity, and that's the main feature of it, but that's pretty much the same as the cosmological constant. So what's really the difference? And of course, Einstein...
Let me tell you the comment about it. On the left side, it was lambda coefficient, some constant. They have to move to the right side and to name it dark energy because there is a matter in the right side of the Einstein equations. They have no choice. They cannot leave this lambda equation in the left side where is the space, and they moved it to matter energy to the right side and name dark energy. That's it. They have no choice.
Okay, so that's a good explanation of it. Okay, so it occurred to me. Now here's where I sort of going to depart a little bit and change gears. Okay, it occurred to me that the description acceleration of the universe means the correct model is a de Sitter universe. So we're back to the de Sitter, which is 1917, which has an empty universe and produces an exponential expansion. Such a description means the rate of expansion is always increasing. Okay, so what's the difference? What's the difference between having dark energy and just using this de Sitter model, which produces an exponential expansion? So they like to use the term exponential expansion. So they're saying dark energy produces an exponential expansion. But here's a much simpler model, this de Sitter model, which produces an exponential expansion. Why isn't this why haven't they verified this is the correct model? Okay, then they say here, but the dark energy force only enters the calculations after the universe is 5 billion years old. So what we've got is something that doesn't have any effect until 5 billion years after the universe is created. Notice earlier that the NASA site used the term 9 billion, so it's not clear to me when this. So it's more confusion. Now, at the de Sitter universe, Wikipedia says, according to the models of inflation and current observations of the accelerating universe, the concordance models of physical cosmology are converging on a consistent model where our universe was best described as a de Sitter universe after the fiducial Big Bang singularity and far into the future. that's a lot of words. That means basically they're admitting it in Wikipedia when they're talking about the de Sitter universe that basically it becomes equivalent to this lambda CDM model, apparently at some point, when it's not really clear. So the point I'm sort of getting at here is, why do we need dark energy if the de Sitter model works? What's that about? Well, the de Sitter model, this is oopsies. If they were to go back to the de Sitter model, they'd have a problem because there'd be no Big Bang. Because the de Sitter model doesn't have any the exponential function never goes to zero. So you can't really have a Big Bang there. Then there's this other thing that's kind of interesting, which is the de Sitter model is apparently, in a way, equivalent to the so-called steady state cosmology. And we don't want that because we've got the Big Bang, we have to have the Big Bang, but that allows continuous creation. So the de Sitter model has continuous creation. Not creation all at once in the beginning. But then you get to the big thing that they don't like, which is they say there's no matter or radiation in the de Sitter model, so it's not physics, it's not a physical model, and so we can throw it away, which apparently is what they've done. Now you're back to the other problem of the de Sitter model, which is that it says that the universe is always flat or Euclidean. Okay, but this they'll find interesting. The measurements that they've come up with, they say the universe is flat and Euclidean. So the measurements done by WMAP and Planck say that the universe is flat. Okay, so that agrees with what the de Sitter model says. So why don't they just use the de Sitter universe model and invent these other things? Okay, this is a repeat of a slide that I had before. Here's the de Sitter model is in blue. You see it doesn't go to zero, okay, on the left. The other models that they're talking about here, this is the pink model, or I guess that's a magenta model, and that's the lambda CDM model, and it starts at 15 billion years in the past. It's zero, so it's got a Big Bang, and then it's increasing. Its expansion rate is increasing, but not as fast as the de Sitter model. Then you have this cyclical model in blue, which is a closed universe. And trying to make sense of all these different models and their terminology is kind of confusion. Okay, so here's another point I mentioned before. The dark energy has been described as having the effect of a negative pressure that is pushing space outward. I don't know what they mean by, this idea of negative pressure is, in my mind, confusing. What does that mean? What's a negative pressure mean? Some scientists think that dark energy is a fundamental, ever-present background energy in space known as the vacuum energy, which could be equal to the cosmological constant. What does vacuum energy mean? I think that idea comes from this zero-point energy. Comes out of quantum mechanics, which would violate Vadimir's rule that you can't mix quantum mechanics and classical ideas. So that seems to be a violation of that rule, where they've introduced quantum physics ideas into what essentially is a classical type of theory. And here's some of my comments about what exactly is dark energy. We don't know. Okay, so they're making a statement, we don't know what it is, but we know that it exists. I don't understand how you can say that you don't know what it is, but you know that it exists. How can you say that it exists if you can't identify it in some clear-cut way? So, to me, this is kind of confusing. And then the term negative pressure, that's confusing to me what that means. I think Vladimir sort of explained the terminology a little bit, but when you read these statements and things, I mean, NASA's supposed to be an official site. They're supposed to be able to tell us what it's about, but now it's confusing. Here's some University of Chicago. After the initial inflation of the Big Bang. So we have to have inflation. So we've got this, so we've got a Big Bang, which you could sort of see as an ad hoc assumption. And then you've got inflation, which is another ad hoc assumption. The expansion of the universe began to slowly slow down. Okay, so the universe has to slow down after the initial inflation phase, but remember now the inflation phase is supposed to be an exponential inflation. There's that word again. And then it stops, and it has to stop so galaxies and stars can form. And that's the key point there. So they need it to slow down so that galaxies can form. And then here's that 5 billion years ago, the expansion sped up again. So the Big Bang occurs, inflation occurs exponentially, then the inflation stops, and the universe slows down, and it's expanding linearly, I guess. And then it starts speeding up again after galaxies have formed. So this all seems to me to be ad hoc. We're going to get off of here. This thing is, we got a few minutes to go. And I made some comments. I find all these statements and explanations to be confusing. Okay, here's the point I don't quite understand. Why don't they just say it's an anti-gravity force? It seems to be an anti-gravity force. Why don't they just say that dark energy is an anti-gravity force? They don't really, this is why I think the terminology is confusing. It appears out of nowhere, and they seem to have to sort of have a mathematical piecewise model, which is, we have an exponential expansion for the inflation, then the expansion stops, and then the exponential expansion starts again after a while. And this all seems to be ad hoc, these assumptions. The model just seems to be put together to in a kind of a kludge, if you know what kludge means. The model seems to be a kludge to me. All right. This is Tim Radford. Tim Radford, who I mentioned earlier, is apparently the science editor for The Guardian, and he wrote an article in 2004. It's kind of interesting, kind of the comments that he makes there. We can go back and talk about Radford. It's going to turn off here in a minute. Yeah, this is the thing. Put simply, space sucks, says Paul Davies, a British cosmologist now based in Austria. And just as pressure creates gravity, so sucking creates anti-gravity. When the sums are done, the conclusion is startling. Space sucks so hard, its anti-gravity wins out. And I'm going like, what are these people talking about? Okay, then I'm going to talk a little bit about quintessence. This is one of the explanations. Differs from the quintessence differs from the cosmological constant in that it is dynamic. That is, it changes over time. Okay, so quintessence, they try to put in this force, this anti-gravity force. It has to change with time. It has to be a mathematical function of time. So the theories of quintessence have that the force is, they put it in as a function of time. So there's a time variable function that is associated with that. And this part is confusing. It can be either attractive or repulsive depending on the ratio of its kinetic to potential energy. Those working with this postulate believe that quintessence became repulsive about 10 billion years ago. About 5 3.5 billion years after the Big Bang. Okay, not sure what that's supposed to mean. And the reason it's called quintessence is because it's supposed to be a fundamental force. So we have 4 fundamental forces in physics. Quintessence is according to their theory, they're going to add a 5th fundamental force, and they're calling it quintessence. And then there's the vacuum energy idea of dark matter is vacuum energy. George Lemaitre kind of comes from, to interpret, goes back to George Lemaitre. I talked about him before. His model actually does seem to be close to what the lambda CDM model is. I talked about that on Saturday. And Edward Tryon in 1973 proposed the zero energy universe hypothesis that the universe may be a large scale, here we go again, quantum mechanical vacuum fluctuation where positive mass energy is balanced by negative gravitational potential energy. And apparently this is one of these vacuum energy ideas. And this seems to me to be this idea of the 0 point energy of the quantum field. And again, this is quantum mechanics getting introduced into what would appear to be classical ideas. And then we have dark energy inflation. I'm going to stop it here because the time is running out. Does anybody have any comments or anything you want to go back to talk about? No takers.
It's common. Because
Excuse me?
there's no experiment proving that it exists. Physics
Well,
is experimental science.
Do experiments really prove that? That's the point I'm trying to get at. I mean, there's other models that they could be using that don't involve this hypothesis that you're going to name something dark energy. There's a, as I pointed out, the Dissident model doesn't really require you to put in an ad hoc hypothesis.
It would seem if the universe accelerates in its expansion, that it would have to accelerate in one direction. Where why don't we see the inertial effects of similar to how, like on a bus, when you bounce a ball and the bus accelerates, you see it doesn't go up and down. Well, I mean, as far it seems that it would be observable other than just measuring the distant stars, redshift wise, or however. I mean, of course, we wouldn't experience the acceleration, like we wouldn't feel the inertial effects on Earth because we're bound to gravity, which we're like a stabilizing force that keeps us bound to the Earth. But it would seem that it would be apparent when we look at the stars and planets and such that there would be that it's difficult to explain. What I'm thinking. Never mind.
A century ago, things like cosmological constant were fashionable, to input into the media. More recently, dark matter and dark energy are sort of fashionable terms to use.
Yeah, well, that was my point when I was mentioning about that Turner's. I'm kind of, Turner says, well, I wanted to come up with an idea that would make it difficult for people to explain. I didn't want to make it easy. So in other words, he didn't. I mean, I thought to myself, that doesn't, it sounded to me like all he wanted to do was make some mysterious term that would get a lot of attention in the media. I think that was the real reason they came up with this dark energy. Oh yeah, dark matter, that's an exciting thing. There's a lot of talk in the scientific news about that. So I'm going to make something called dark energy. And we'll bring that up. And that'll be even more exciting. But I think is that guy Tim Bradford, when he talked a little, I think he sort of expressed it kind of like, this is like, something we don't understand. we brought two things into the scientific discussion that we don't know what they are, but they've got fancy names and they just inspire. We don't. It's just. He says that dark energy is unimaginable. To me, it's sort of like I can't imagine what they're talking about. That's kind of my point. Maybe you can imagine what they're talking about, but after reading, a number of these different articles, I didn't really have any more of an understanding of what they were talking about than I did before I read the articles, and I was actually even more confused and more mystified.
But it's worked because the media are agog with all these terms. Whereas if he introduced things like negative pressure gradient or something, they wouldn't have been interested at all. But these are the terms that have really rung bells.
Yeah, the term negative pressure completely confused me. That's another. I went to Wikipedia and I did a search on negative pressure. What does negative pressure mean? It says it doesn't exist. Negative pressure doesn't exist. So
I think he's thinking of not compression, maybe tension. It's a bad term, but I think that's probably what he's trying to get at.
Well, I think what they mean, I can go into this even more. So here's kind of my summary of it. The concept of dark energy adds complexity to an already complicated list of cosmological models. So we got a lot of these models and a lot of these ideas. If you, and I didn't even talk about this. You got these parameters. You got these acceleration parameter. You got density parameters. You've got all these symbols. And one of the things I learned when I started looking at cosmology books, different books use different symbology, and then that's no big deal. I'll just look in the section where it tells you what the symbols mean. Well, they don't have a section where it tells you what the symbols mean, so it's very confusing. I guess the new books tell you what all these symbols mean, but when I showed the chart, this thing here, there are these omega A equals 1, omega M equals 0. All these, what do these things mean? It's not really clear to me. What all the and when you start looking at the Friedman models, they use K equals 1, K equals 0, K equals -1. I'm not really sure what K means. I'm not sure if K is the same as omega, and it's just very confusing to me. And I have all these books, and I read a lot of them years ago, and my memory is not that great on what all this stuff means. So it's confusing.
Omega is the ratio of energy density to the critical energy density. That's it. If you have your critical energy density, omega 1 equals critical energy equals.
It's just to find where the definition is, and so that you understand what they're talking about. It's kind of unclear.
Most important, if you are talking about accelerating expansion from what point? Where the center of the expansion? The beginning of the story. Where the center of expansion?
I'll talk about that a little bit later. I think that's one of the issues that is not real.
It's a critical issue because there is no, and what is important, there are over 8,300 blue shifted galaxies. What we're gonna talk about? If there is an acceleration of expansion and even Andromeda moving to us, and that's a simple one contradiction immediately. Where is this expansion? Where is the accelerated expansion?
Well, how many blue shifted galaxies? I want to take note of that. How many blue?
told you blue shifted, it's already in catalog. In 10 years ago, it was 8,300 blue shifted galaxies. It's not only one Andromeda, all of them. How to put into the expansion and especially accelerating expansion of these galaxies?
Yeah.
Well,
I would count them.
okay, so
from the very beginning, it's a nonsense. From the very beginning, if you're talking about expansion, show me the center of expansion. That's it.
all right.
And then start to talk about something.
All right. Well, we can shift to the next. Are you familiar with? Have you ever seen this book? I bought this book. This is called "The Time, Knowledge, and the Nebula." And have you heard of this book? Time, Knowledge, and the Nebula by Martin Johnson. It's 1947. I bought this book at a used bookstore many years ago, and because it said, and the nebula, it says time, knowledge, and the nebula, and I thought to myself, well, that's really interesting. I'm interested in nebula, and then I bought this book. It was $3.50, and I opened it up, and I started looking at it. It was all mathematics, and I thought, well, it doesn't tell me anything about nebula, because I was interested in galaxies, because I'm an amateur astronomer, and I'm interested in galaxies. So I put this book in a box and forgot about it, and it was only within the last couple of weeks when I was going through boxes and looking to see what I had in the boxes that I pulled this book out and thought, oh, this is an interesting book. Maybe I ought to take a look at it. And it talks about Milne's cosmological theory, okay, and De Sitter's theory. So what's interesting about this book is because it's old, it kind of tells you a little bit more about how these theories developed. And the Einstein and De Sitter and Lemaitre, and then he talks about Milne, okay. And have any of you heard about E.A. Milne's kinematic relativity? Nobody's.
I don't think so, but it rings a bell, I think, Harry.
Yes. He wrote I remember years ago, I guess maybe in the 90s, around year 2000, I borrowed a copy of his book, Kinematical Relativity, from one of the government libraries that had a copy of it. And I thought, well, this was back when I was just starting to be interested in relativity. And I tried to read it, and I couldn't understand what he was talking about. Okay. And this is an example of alternative to Einstein's relativity that kind of basically people decided this isn't interesting. It doesn't agree with what Einstein says. We've already proved that it's wrong, and so therefore we'll ignore it. And so it's kind of, some stuff that's kind of fallen through the cracks, so to speak. Do you understand what I'm saying? And so this book here that I'm talking about is kind of an attempt to explain Milne's theory, basically, is the bottom line of it. And his theory is kind of interesting because he focuses in on what does it mean to say that space expands? What does that concept mean? Okay, and so he's got a section in here where he says there's a bunch of different ways that we can, interpret what this concept of expanding space means. He gives 4 different interpretations. And it's kind of interesting. And one of the interpretations is of the redshift is, suppose time is changing and not space. Okay, and he says that the Sitter model is based on that. And I go to my, and I, when I heard this, when I read this, I thought this is very confusing because the, this thing here says that the Sitter model is space expanding. Okay. And in the book here, he says, no, the De Sitter model says time is changing. You're shaking your head down there.
You know, all simple logic. Please put me a hypothesis and then follow your own hypothesis. If for one word there are two explanations, I cannot get it. I'm sorry.
Okay. Well, anyway, the point is that what is meant by expand, there's not really, they haven't really proved that space is expanding. Okay, that's the point. The point is that's just an assumption that they made somewhere along the line, and it's not really clear exactly when that assumption took over. Probably when they decided that the Friedman models were correct. Okay, and the Friedman models involve an expansion of space and absolute time. Okay.
But by the way, the same observation could be made as you've made, Harry, with regard to the Lorentz transformations and the scale change. I mean, if space is expanding, well then everything is expanding, including the measuring rules that we use. So we don't perceive that anything is different. Everything is moved by the same expansion rate.
Yeah, the problem is that they don't, when you get down to the, see, this is kind of the point I'm trying to get at. They don't assume that everything is dilating the way they claim. They're still assuming that there's an absolute Planck limit. So the Planck limit, the Planck scale, at some point when you take these models back, okay, and they go down to the t equals minus 15 billion years here, okay, that's where the Big Bang occurs. There's some, at some point they're saying there's an absolute nature of space. Space has an absolute smallest limit. And it seems to me that to say that space has an absolute smallest limit is a kind of additional assumption that they put in there that they didn't really tell us that they're assuming that. Okay. And why do you assume that there's a Planck limit? So as they go smaller and smaller and smaller, the atoms aren't changing their size. Okay, they're assuming that atoms are staying their same size. It's just space is getting bigger and bigger and bigger. The distance between atoms is getting bigger. But they're assuming, and this is kind of, you know, you can criticize that I'm wrong in this, but it looks to me like they're making assumptions that there is an absolute, that space has an absolute nature. And they're also assuming that time is absolute as well. And it seems to me those two ideas that are there are completely negated by Einstein's theory of relativity. So how can you use Einstein's theory of relativity, which says space and time are not absolute, or that's an implication that they tell you when they teach you about it, and yet here in cosmology there's these hidden assumptions of absoluteness?
I would say that time and space are absolute. Space is emptiness, I think. I mean, I don't think space could expand. I mean, what is there to expand? It's emptiness, you know?
Harry, you're absolutely right. It was my question. Our universe is practically infinite. And what does it mean, expansion in infinite space? I don't understand even the definition of it. Expansion of what?
Well,
it's over 93 billion years, light years. You know, size of the calculated universe. What is expansion means in such a big, big space? What does it mean? Even the word expansion, I don't understand it.
Well, what they, well, yeah. Okay, let me talk about this a little. I have a little, all right.
Let's continue some other issues because you know it's a bullshit.
I mean, the old chestnut arises. What is it expanding into? You know, if it has a finite size, and then outside that there's nothing, well, how is it expanding into nothing?
And why isn't that nothing part of the universe?
That's why there are theories that the universe doesn't exist. I saw even such, you know, papers. It doesn't exist. It's our imaginations. That's it.
Yeah, well, that's kind of contrary to the scientific concept. I see that I don't see that Bob's here. Bob is oh yeah, Bob's here. Well, his picture is blank. Bob's more interested in philosophy and could probably, you know, I noticed he mentioned that he's a dualist.
Yeah, I'm here. The whole I'm still here. My screen's a little messed up.
Yeah, this kind of the philosophical aspect of, you know, there's the idealist, as I understand it, say that everything is in our minds. There's nothing that's actually real. Everything is in our minds. But that's not the scientific view of the world. Scientific view of the world is that there's a reality that's outside of the mind.
Yeah, I think you'll find most scientists are materialists, but I'm not. I am a dualist. But.
Yeah, I'm not really sure exactly what that means. You know, these philosophical, you know, it turns out that, you know, that talking about this is difficult because of different people have different views. All right, I'm going to talk about the Sitter universe. When I traditionally,
Yeah. Do you know the distinction between the phenomenal and the physical? The phenomenal is like sense experience, and that's mind.
yeah, that's another distinction. I'm not an expert in philosophy, so I don't really understand these distinctions very clearly. I'm not even sure what my view is about what my philosophical approach is to science. And to a certain extent, I don't even know that scientists do.
Yeah, it sounds like you're sympathetic with Karl Popper, who was a philosopher.
Yes, I'm kind of sympathetic to that because I think that modern science, in the case of dark energy and dark matter, these things are not falsifiable.
I mean, I partly agree with him, but.
Excuse me? Anyway, my point is, I don't really see that I brought up the guy's his criticism of dark energy, and the whole idea is that they're not falsifiable concepts, and you know, so therefore they're not really valid. But scientists don't really take such philosophical criticisms to heart. Everything from their point of view is, can I demonstrate it by an experiment, even, you know, and if they can create an experiment or create an argument that they claim proves something is so, then they just go and say it's so because we've got an experiment that says so.
Yeah, but it doesn't prove anything. It just shows consistency.
Right, exactly. And that, anyway, so I want to talk about Dissident because I find it kind of interesting in that it's not really clear to me that people, based on what I've read, there are different interpretations about what his model is and how to interpret it. Like, for instance, in the book that I was talking about, which is Milne's theory, and Martin interprets it to mean that De Sitter's universe, time is changing. Time is expanding, if you will. Okay. Instead of space expanding, time is expanding. So the way he presents it, he says, well, there are these two opposites. Einstein's idea was that the space was curved, okay, and so the universe was curved and closed, and De Sitter's idea was that time was what was curved, okay. So the two so there's a duality of the two different viewpoints of De Sitter versus Einstein. Einstein, space is curved, but time is linear, and De Sitter's viewpoint that space is static and flat and Euclidean, and time is the curved or changing exponentially. And in De Sitter's view, that explains the redshift that we measure, because when we go back in time, the time is not running at the same rate in the past as it's running today. And so that explains the redshift, and so we don't need an expanding universe. But all this is kind of confusing. Okay, so anyway, he published a series of papers, and this is in 1917, where it's not just where he talks about the universe. He basically is talking about general relativity. It's all based on Einstein. So De Sitter is an Einstein proponent. We'll see that later here, where he basically published 4 papers in which he destroyed Britz's theory, ballistic theory of light. Most people probably heard about this, and some people have been trying to get around this objection that De Sitter came up with to the ballistic theory. But De Sitter cosmology is flat Euclidean space, infinite and not bounded, mass-free and infinitely expanding, and has no origin in time. Okay, so what does that really mean? It's not, the important part is, I think, is that the current models kind of come to the conclusion that space is flat and it's infinite, and it looks like it's not bounded. Okay, so why do we need a lambda CDM cosmological model if it really basically boils down to being the De Sitter cosmology? After you look at what it's saying, it says the current thinking is we live in a Euclidean flat space. Okay, that's what the De Sitter model says. It's a model of Euclidean flat space. So why do we need a lambda, this complicated model with ad hoc dark energy, dark matter, when the De Sitter model does just as well? It says the same thing. I talked a bit about this before, where he did the 1913. He published these 4 papers that demolished Ritz's theory. Then he published a big 3-part paper in 1917 where he introduces his model. And then this is another part that's confusing. There's another model called the Einstein De Sitter model, which to me, I didn't understand the difference. But apparently in 1932, he got together with Einstein and they co-authored this paper. And this paper described what's called the Einstein De Sitter cosmological model. Now, it's not clear to me whether the model that is described in this diagram here as the de Sitter model is the Einstein de Sitter model or the de Sitter model. You see how complicated this gets? It's very confusing. But I'm going to go on this is the de Sitter model. It doesn't have any t equals 0. Okay, so there's no space goes to 0. There's no the space time goes to 0 at t equals 0. It just gets smaller and smaller and smaller. It's an exponential function. So it never goes to 0. It never completely shrinks up to 0, and it is continually expanding. Okay, whereas the currently accepted ideas have a thing where the time goes to 0 and the space contracts down to a point, and so you can say that's a Big Bang model. Okay, Einstein wrong again. This is a really kind of a catchy idea I came up with. Einstein believed that the universe was finite with curved space. Now it's kind of interesting. I have this book, The Meaning of Relativity. He talks about this in his book. He also published a number of papers. So Einstein believed that the essence was that space was finite and curved. And I think that idea sort of dominated a lot of physics thinking pretty much for many, many years. Probably still dominates physics thinking. Because you'll see in books, the universe is finite, it's curved, and I have a lot of books on cosmology where they all make this argument and statement. The de Sitter space is Euclidean, flat space, so that's what the current claims are. So Einstein's wrong when he said that the universe is finite and curved, because the measurements that WMAP and Planck are proclaiming, they say it's flat space, which means it's Euclidean. So Einstein was wrong about that, it looks like. So now that we've proved that Einstein's wrong again. And of course, they also claim that he's wrong about the cosmological constant. Of course, they've been saying that for a number of years, but that's another place where he's wrong. So Einstein wrong again. All right.
No, he's wrong or not, because hypersphere is a finite space. Hypersphere is finite without boundary, no boundless.
Well,
and it's curved in a fourth dimension. If he means in third dimension, I don't understand it, but in the fourth dimension, it's curved and finite. I'm sorry, I'm not following Einstein. I didn't know even about his idea that it is curved and finite. But hypersphere, guys, and hypersphere as a world was, oh my goodness, about 180 years ago, the idea of such world by a mathematician.
The point I'm really making there is that I think that because Einstein asserted these things, and that people sort of, because Einstein said it and he's the great man, therefore I'm going to believe what he said. And I don't really, it's not until recently that they've, the Hubble constant has only been nailed down to, fairly close agreement, and I talked about the Hubble constant and different opinions about how, what the Hubble constant was, and it was really wide range of opinions about what the Hubble constant was. Now it's kind of narrowed down, and so they can sort of make their measurements and kind of deduce things about what the measurements mean that have maybe more confidence than they had in the past. Back in the 30s and 40s and 50s and 60s, even into the 70s, all this stuff was still speculative. Cosmology was empirically speculative. And so now they've reached this transition where it's not empirically speculative. They've sort of been able to nail it down with measurement a lot better than it used to be. And to me, it's ironic that they come up with this conclusion that space is flat and Euclidean. And, for years and years, they were trying to tell us, no, it was curved and finite. So I just find that it is interesting and a change in viewpoint.
The next very important point Einstein told: without matter, there is no space, time, and gravitation. You cannot put even these notions without matter. It's exactly my point. Without medium of the world, we cannot even start talking about time, space, and gravitation. You see, I like this, but he always stated this, conclusion. But I found in my model, I explained where is time, where is space, where is gravitation in the medium of the world. There is no medium, there is nothing. This is my point.
Right, I understand that. And it seems to me that they don't, as I was trying to explain earlier, where I said, well, what they've done is they've grafted quantum mechanics onto these general relativity models that were developed. So the general relativity, I'm going to talk a little bit about this. The general relativity models, it looks like Dissident and Einstein came up with models before 1920. I think Friedman kind of came up with his idea about the same time, I think before 1920. But Friedman, they didn't really pay much attention to what Friedman was saying, the Friedman models. And they, from what I gathered, became kind of popular later. Okay, and so up until 1960s and 70s, this cosmology was all just based on the idea that it was a deduction from general relativity, and general relativity is, of course, in some respects, classical physics, because it makes classical physics assumptions about space and time ideas. But I think when the Big Bang comes in, that brings in quantum physics ideas, and so the idea of the Big Bang is essentially taking quantum physics in the form of particle physics ideas and grafting them onto the old Friedman models, which had time starting at t equals 0. And so, because the Friedman model started at time equals 0, now notice that the Dissident model didn't have time going to 0. It had a time exponential, an exponential function of time. So space never contracts to 0, but in the Friedman models, it contracts to 0. And so the Friedman models became adopted, this is my theory about it, because they allowed the space variable to contract to 0, and then that allowed them to bring in the particle physics idea, okay? And so they grafted particle physics onto the Friedman models and that became called the Big Bang model, okay? And the only reason that they could do that was because space had to contract to 0. And if space doesn't contract to 0, you can't use the quantum mechanic Big Bang idea, the idea that particle physics explains the origin of all the elements in the universe. That can't be grafted on to the cosmology unless you have a space contracts to zero concept.
Point about Friedman equations. Let me tell you, Friedman equations done with space filled with perfect fluid. There is no vacuum in Friedman equations. There is some numbers, pressure, and mass density, and all this stuff. How come? Do we have vacuum or we have a perfect fluid according to Friedman? One more contradiction. You see what I mean? All of them contradict each other, you know, all of them. There is no vacuum or there is a vacuum. Simple like this.
Yeah, that's kind of my. I kind of tend to agree with that. But here's the point I wanted to make. This confuses me about these models. Why is the space expanding when gravity is an attractive force? I don't understand that. Why is the universe expanding when gravity is an attractive force?
I guess they would think from the initial explosion of the Big Bang, the initial singularity exploding. I guess that's what I think causes the expansion. I guess.
Well, right. Well, you know, I guess that's what. But then that means that it's dark energy that's causing the universe to expand at the initial Big Bang, right? But
well,
they don't.
It makes it go faster, I guess.
Well, it seems to me that if you, yeah, I don't really understand, you know, why dark energy isn't invoked in the initial Big Bang. It's something else. Okay, well, so to me, that's why I think that they've created the piecewise mathematical models. So at the beginning, what causes the Big Bang? You know, that's essentially a particle physics model, which is essentially quantum mechanics. Okay, so you have a model that describes the initial Big Bang, and then you transition to, during this Big Bang, you transition into the inflation era, okay, which is another kind of an ad hoc add-on. So there's an inflation era that follows the Big Bang, and then the inflation stops and the universe slows down, and as far as this expansion is concerned, and that's when the era of galaxy formation comes in. And then later, after galaxies have formed, then the universe starts expanding again, okay, due to dark energy. And all this seems kind of ad hoc to me. It doesn't seem to be one consistent model. It's just a model it's a patchwork model of different pieces that cover different eras of time that they put together and stitched together and called that a cosmological, a scientific theory. Anyway, I've sort of finished talking about what I was going to talk about. It cut me off just at the end of my little dissertation there.
In my model, there is no expansion. There is stretch. It's a totally different phenomenon.
Well, I see your model is closer to the Dissident idea, to be honest with you.
I didn't know about the Sitter model. Believe me, I was not expert as you in history of cosmology. When I started, immediately I neglected dark energy, immediately because it's bullshit. The second point, you know, I saw contradictions of the standard model. And there is a vacuum or there is no vacuum, and so on and so on. And I started everything from the beginning, from the classical physics, before Einstein, before all these bullshits we have right now in cosmology. That's it, simple like this. Neglect everything and start everything from the beginning. It was my point 24 years ago.
Because isn't the sitter starting from the premise also that the red shift is a Doppler shift. And I mean, if so, they're starting from the wrong basis.
It doesn't matter. I don't have redshift in my model at all. I'm very sorry. That's why I don't know what they're talking about. I don't know how to measure distance according to redshift. I don't know. I don't know this graph, what we saw today, Perry showed me. I don't know how to split redshift and distance. I don't know. They put in distance this behavior of a few stars or galaxies, you know, and that's it, simple like this. It's not right. The logic is you accepted redshift, you want to measure the distance according to redshift, but they wanted to do redshift separately and distance separately. How they could measure distance? I have no clue. With suggested that the galaxy's behavior is the same, the brightness the same, brightness the same of all these galaxies around. No, how it could come to
some
somebody.
galaxies are blue shifted. That's true. Like the Andromeda would be the near example, but it does appear from what I've been reading anyway that there is some relationship, proportional relationship. I don't think it's linear. Some proportional relationship between distant galaxies whose distances are obtained by Cepheid variables and other means and so on, and the redshift. There seems to be some proportion that the further away the galaxy is, the greater the redshift. Now, if you look, well, I maintain, as I think you know, if you look at this in terms of energy, that's not surprising. In fact, it would be very surprising if the contrary didn't obtain.
Now what? For me, we have right now GWST, 100 times more powerful than the previous telescope. And if we didn't see with the previous telescope something, and we can see it right now, it means for me it's further. How much further? I have no clue. But you know, for me, more powerful instrument, further you can see. Simple like this. Without Z, for me it does matter, because in my case, in my model, there is no Z at all. I didn't measure distances, no. Even the transition from one station, dark epoch, to light epoch, depends on some definitions, not on my model, because age of the world, 14.22 billion years, and that's it. It's calculated based on gravitational constant, and gravitational constant we can measure on our Earth. Simple like this. That's why, you know, we should cancel all these ad hoc notions. Dark energy, measurement of the distances, all this stuff. I don't know. I'm not an astronomer. I don't know how to do. I cannot even propose them some method how to measure these distances. I don't know. But what is important, if we have 8,300 galaxies blue shifted, then what kind of expansion you're talking about?
Well,
that's why
my point is that that's not exact. It's not exactly clear what they are assuming. Okay, they're assuming the two pillars of modern cosmology. One is that the universe is expanding according to the Friedman model concept. Okay, and the other pillar is that by grafting quantum mechanics onto the then they can explain the creation of elements and the Big Bang and cosmic microwave background. So the cosmic microwave, so the two empirical facts are that they observe the redshift and they observe the cosmic microwave background. Those are the two facts. And from that, they've grafted on this very complex cosmological interpretation.
I've often thought that if the universe is expanding, that it's possibly a local expansion caused by a local cosmic explosion. Of course, the expansion is astronomical, but why couldn't that explosion have occurred in a universe that already existed? If it appears to be expanding, which if it is expanding, what's to say that countless light years away, that it's static or something else.
Well, I don't believe that you asked me last week, I think, whether or not I believe the universe is expanding. I can't say definitely for sure, but I'm not convinced that that's the case. So the real issue is if you buy into the idea that the universe is expanding, then you sort of are forced to buy into a lot of the other ideas. The dark matter, the dark energy, the Friedman models, the Einstein. So really the really big issue is, do you buy into is the universe expanding idea? And that's really the crucial fundamental. Do you believe that is empirically proven? Okay, science is based on empirical facts, observational facts. So if you accept that idea, then now you're going down the road of modern cosmology. And but what happens when you go down that road is you get involved in a lot of these contradictions, which they don't want you to perceive them as being contradictions. So everything is presented in terms of, well, these are facts because we've demonstrated scientifically, we've observed them to be facts. Things like dark energy exists, dark matter exists. Dark matter exists because, well, we've got factual evidence that suggests that it exists. And then they have a theory that requires that it exists. Okay, I talked about that last week. Their theory of inflation requires that dark matter be produced as a result of the inflation. So now they have a theory that requires dark matter to exist, even though it was really just an ad hoc assumption to begin with. So this ad hoc, mysterious entity suddenly now becomes an actual factual entity. If you believe the way they're going about doing science. If you have free will and you don't believe that what they're doing, then you wind up like Vladimir.
Let me tell you, dark matter, they suppose or they know that there is so-named gravitational lensing effect, and they can explain it by dark matter experimentally. And the very first Tweety, he measured the dark matter center of supercluster, and he found that the mass of this center at least 300, 500 times more than we have in our Milky Way galaxy. That's why these two experimental results show that it exists as a big bodies, something very big one. But they don't know what are the particles or what are these dark matter particles inside of these big bodies. That's why they accept already the existence of dark matter by experiments, gravitational lensing, and center of superclusters.
Well, in my view, that's just a contradiction. It's just, something's wrong with physics, and they invented this dark matter to explain the fact that the contradictions exist. So it's a hypothetical entity that must exist because otherwise our physics is proven wrong.
Yeah, oh yeah. Even this, creation of all elements depends on them. You're absolutely right. They invented, they cannot do anything without. And they, from one side, they're talking, dark matter doesn't exist. From the other side, big bad matter doesn't exist without dark matter. Where is the logic? Guys, exist or not? That's why, all the contradictions inside of the standard Big Bang model, so many contradictions. That's why I don't know what they're doing, these professors, these, famous physicists, cosmologists, how they can take it. All this absolutely illogical, model.
But they're true believers. I think that's really the Einstein has this theory, okay, special relativity, and then he said special relativity doesn't really make much sense, and we've talked about that. I mean, CNPS has just beat the heck out of that. And so then you have general relativity, which is an extension of special relativity. And then Eddington says, oh, I proved general relativity is correct. And then they have this business with the perihelion advance of Mercury. Those are I guess there's something else. I forget what the third pillar is. That's pretty thin stuff to basically construct an entire new ideology of science on. But it's an ideology. It's general relativity is correct. And so then guys like Dissident come along, and notice that I made a real big point of pointing out that Dissident basically went to town to destroy the ballistic theory as a competitor to special relativity. So he made sure that he completely disproved the Ritz theory before, and then he proceeds to adopt, he's adopted the Einstein theory. And at this time, it's brand new, and so he can forge on and make himself famous by inventing this, and he comes up with this cosmological model, okay, and so these guys are basically creating theoretical entities out of mathematics. That's really basically all it is. And then they're hoping that this will be, some empirical evidence will be found that will prove their theory. And of course, there was already out there when they got this expanding universe data. And so they just grafted the empirical evidence onto their theory, and that's kind of what their process is. But it seems to me that, and this was my point that I was getting at, the cosmological theory of Friedman assumes that time's absolute. You have to have an absolute time, a universal absolute time. But Einstein's theory says that time's not absolute, so that's a contradiction. Okay,
yes.
Then, and so it's just, the whole cosmology, then people say, well, the cosmic microwave background radiation proves that there's an absolute frame of space, that space is absolute, but that's not supposed to be a conclusion that is acceptable in relativity as far as I can see. So that's confusing. So how can you, it's just, to me, it's just all just a lot of confusing stuff. And that's kind of my view of it. I find it confusing.
Yes, you're right. But let me finish with dark matter. 200 years ago, Mitchell, he predicted existence of binary stars. 108 years after him, we found these binary stars. There are some dark stars, and it's already experimentally proved. And what is important, very famous classical physicists like Poincaré, Lord Kelvin, and all of them, they not only believe in dark matter, they calculated this dark matter, how much you have, they're close to the visible matter, invisible matter. All of them were stupid? No. Dark matter does exist. Dark galaxies, right now they open dark galaxies. There is some galaxy and there is some companion of these dark galaxies, dark galaxy, and nobody can see it. It's invisible. That's why, no, I am against everything what you told us about this cosmology, about Big Bang model, about Friedman, and all this stuff. It's always no logic at all. But dark matter, for me, it's a confirmed experiment, proved idea that it exists. Important, they don't know what dark matter means. I mean, what kind of particles you have inside of these bodies. There are dark stars, and you know how many dark stars already they open? By X-rays, you know, they found these dark stars by X-rays radiation, not visible spectrum. They're invisible, but with different wavelengths, you can see.
If it's if dark matter is detected through X-rays or other electromagnetic spectrums, why isn't that obvious proof? Why isn't everyone convinced? I mean, I'm not saying that it isn't. I just don't know.
It's invisible. If you're looking in a standard telescope, you cannot see them. You can see that this is galaxy, what you can see, moving. It's a binary galaxies, binary stars, binary. You can see center of the mass, and there is no the other mass. This is simple like this, guys. That's why, as for dark matter, you know, please don't touch it, because for me, what is important, it's not dark, it's invisible. Invisible. It's dark because it was a telescope only. Right now, we can see all the electromagnetic range from gamma rays to 21 centimeter radio waves. And we can prove the existence of these objects experimentally.
Well,
that's quite different from their conception. You know, their conception is that this is an unknown. As you've said it, in fact, Harry, it's an unknown quantity. We know nothing about it. But all we know for certain, 100% certain, they're so arrogant, that it exists. Because the theories which have, you know, spectacularly proven their worth by experimentation are so certain that you need to postulate this to save the theory. So it's really an arrogance. But it's not what you say, that it cannot be detected. If you see a boat moving away from you and it goes away from the horizon and it disappears, you don't say that it's a dark ship which is disappeared by some other means. You accept that it's always there and we cannot see it because of the curvature of the Earth. That's quite different from saying it's dark.
Talking dark, invisible is correct. You exactly, it's a very good point you done. But if you will use radio waves and radio telescope, you will see the ship even over the horizon. Simple like this. Guys, dark, it's not dark, it's invisible. This is my main point. That's why, you gave a very good, example. Invisible, yes, but put a telescope or measure this ship over with satellite, and you will see it immediately. No, man, it's a very good example you gave, Ivan. Thank you so much. No, guys, dark matter. I accepted 24 years ago. I accepted this notion, dark matter, but dark energy is a bullshit. Man, it's unbelievable how bad it is. And they insist, and 70% of energy density inside of universe unknown. How you can build any theory if you have 70% of it unknown? It's unbelievable.
Well, here's another issue for me. My issue is I don't understand why ether doesn't exist, but dark matter does exist. It seems to me they're kind of the same thing. It's a hypothetical entity that is needed to explain physics, but they'll say ether doesn't exist, but dark matter does, but they're both hypothetical entities needed to explain phenomenon in physics.
Exactly my point. Medium, it exists, and there is all these dark matter particles inside, so named dark matter. Right now I have universe created matter. It exists inside of the medium. Simple as it.
Again, it's dark.
That's why there is no vacuum. There is a medium of the world. You can name it ether.
Yeah, but you see, for whatever reason, the ether became a no-no. It was associated with superseded theories of the 19th century, and Einstein disproved it. So it's a no-no. I told you about this professor who was reported to me by one of his research students, who actually accepted an ether. But he said that if that became public, he would lose his job. But dark matter, on the other hand, contrary to that, is fashionable because it was introduced in modern times, post the modern cosmological Einsteinian theories and so on, and it's necessary, and the media have taken onto it. So you're right, Harry. Yeah, they're just maybe different sides of the same coin. But one is heresy, and the other is orthodoxy. That's the simple.
Well, I don't think that dark matter would exist, that it wouldn't exist uniformly. Whereas ether is supposed to be continuous, like covering all of space, as I understand it. Just a thought.
Yeah. I just, to me, I just, there are too many contradictions.
Which theory without contradictions? Your opinion?
I just sort of, I can't understand why, if you can accept the existence of dark matter, then why can't you accept the existence of ether? Why aren't they the same thing?
Told you, I have the medium of the world. You can name it ether. That's it. Simple like this. Yes, it's a bullshit vacuum. It doesn't exist. This is was critical for classical physics to cancel ether. Ether is a totally different story. That's why dark matter exists, invisible matter, and ether exists. But I saturated this ether with its particles, with some content. Because what does it mean, ether in standard understanding? Some kind of perfect fluid. What is this? What is your understanding of ether? What is the content of it?
Well, it depends on who you're talking to.
You? What is your understanding of ether?
I don't believe in ether. I believe that space has properties, and the issue is that we don't really, instead of attributing, like say for instance, these mysterious phenomenon, instead of attributing them to a change in the characteristic of space, we say there's dark matter there. That's my view of it. So dark matter is just space, okay, but space doesn't have the same characteristics everywhere. That's my view. That's my simplistic explanation of it.
Okay, you have your binary stars. They experimentally proved. What is your understanding of binary stars? Predicted 200 years ago.
Well, I'm not sure. I mean, binary stars, it turns out that the majority of stars are multiple. And so binary stars, there's binary stars, triple stars, quadruple stars. They go down in probability the more of them that you have. And then you have stars and planets. So it looks to me like, God's plan is that he has stars and they have objects revolving around them. I'm not sure what your question is, but my idea is that space is, we don't know what space is, and so that's really the problem.
Then we have nothing to talk even about. There is no space, there is nothing to talk about. I mean, universe, it doesn't exist.
Well,
yeah. I think that everything physical exists within space. That space is just an empty void that may be filled with, physical phenomena.
Well, that's the common solution. This goes back to the argument between Aristotle and what are called the materialists, Democritus and Leucippus, and they said that space is a void. They said that the world consists of atoms moving in the void. Okay, so space is just nothing. It's void, nothing. It's just an abstract nothing idea. And modern science adopted that idea as opposed to Aristotle. Aristotle thought that space was a kind of a medium. And so there's your dichotomy right there. And so that's never really been So they kind of, the Newton, and there's a big argument there, beginning at the origins of science. Leibniz, Descartes had this vortex theory of gravity, and the idea was that there's some kind of an ether that surrounds the sun that's in vortex motion, and it carries the planets along with it. Okay, and Newton said,
I might suggest that if there is an ether that exists sort of over empty space, that it occupies empty space.
That's the common idea. Most people want to add some kind of something to space. So ether then becomes some kind of a particulate, some particle that exists. Okay, and that's kind of the hang-up. As soon as you postulate a particle, then you have to go find the particle. This kind of is the problem with dark matter. Where is this particle, and where does it fit into the standard theory of particle physics? They haven't been able to figure out what this particle is and where it fits into the standard model.
Well, I would say space is inherent. If nothing existed, I think time would go on, and I think space would just be an empty void. However, though, there's the presence of the universe, which exists over the empty space. That's just number.
Well, that's a lot of people think exactly the same way you do.
I haven't found many.
Well, I mean, that's the scientific idea is that space is a void nothing, and that's a problem. And so you get this. The ether sort of resolves the problem that space is a void nothing because it gives space properties. So now space has properties if you put an ether in it. Okay. But what is this ether that you're putting in space? That's really where the problem is. And that's the problem with dark matter. What is this dark matter thing? Let's find it. How does it fit into?
Many think that the ether is a physical entity, and many consider the ether to be space. However, though, I think if there is an ether that exists in space, especially if it's physical, I mean, it occupies space. I would think.
Absolutely right. There is no medium, you can name it ether, there is no time, there is no space, there is no gravitation. It's exactly the main points of my model. Space is a result of the medium. You have air around. Without air, without ether, you cannot introduce even this notion. That's why, Jerry, you're absolutely right. I'm sorry.
So you're saying that space is separate from the medium of the world?
I would definitely say so.
You have no medium, there is no space. There is no space, there is no time. I have in my model T02. It should be some time to grow up this bubble in the universe, small one, to introduce all these numbers. You know why? Because we should have the medium, classical notion. And classical notion means ensemble of particles. Before this ensemble, before the medium, you have nothing, no time, no space, nothing. And Jerry, he's absolutely right. Ether or medium in my case, it's the beginning of everything. Time, space, and gravitation. Simple like this. Before nothing. Before it was only eternal universe and that's it. That's why, you're absolutely right, guys. I'm not against you. On the contrary, in my model, it's inside of my model. Inside. There is no space. You cannot talk about the void, space, empty space. There is no empty space. There is only medium. And characteristic of this medium, it's one of them space, another one time, another one gravitation, and it's a different values of this medium. Suppose the gravitation, it's energy density of this medium, then you can go with gravitation. And Hubble parameter, it's a so-named parameter for the medium. If you have your medium, you have sound going through the medium. It should be some characteristics of this medium. That's why we introduce all these notions only when we have classical object named ether, or in my case, it's the medium of the world. Simple as this. That's why don't talk about all these notions without matter, without medium, not even matter, not particles. It should be medium. Air, sea, water, whatever. Medium of the world is a savior of everything, including these very important notions: space, time, gravitation. And I told you already, Einstein, he claimed it, that they cannot exist without matter, without any description. What does it mean? In my case, matter is the medium of the world, classical notion. And only for classical notion medium, you can introduce this space, time, gravitation, only for the medium. There is no medium, nothing. Don't even talk about empty space.
I have sort of the maybe outlandish view that that time and space aren't dependent upon the existence of physical phenomena. That if there's nothing, time and space would go like they would exist. There aren't physical phenomena though, time and space. They're, of course, something very different.
This is the parameter. If you have the medium, there are some changes in this medium, and to describe these changes in the medium, you have to put time, you have to put space and gravitation. It's a properties of the medium. You're absolutely right. All of them you told. Oh, there is nothing, there is no to talk about. Yes, it's exactly the point of my model. There is no medium. There is no classical object named medium or ether. Then you have nothing to talk. Nothing to talk. There is nothing. It's a different properties of the existence of the medium of the world. No medium, nothing. I'm so sorry for my emotions because I'm trying to get the right point. And Jerry, you helped me. You told exactly what is my model about. That's why you don't talk about empty space or something like this. No. The main problem created by Einstein, he cut this ether, there is no vacuum, and that's it. But Friedman introduced this so-named perfect fluid. Come on, guys, it's a vacuum or it's a perfect fluid? I don't know which one is correct. But what is important? Correct answer is no medium, no classical physics, nothing to talk about, nothing. It's a properties of our medium, space, time, and gravitation.
Well, my view is that this is the main point. This is the problem here. Einstein is wrong. I think that's what the agreement is. Einstein, when he brought in this relativity thing, it really just messed up classical physics, and physics has sort of been on the wrong track ever since. I think that's...
Yes, they got this ether and immediately it's the wrong way. 100 years it was the wrong way. With vacuum, with perfect fluid, I don't know with what. I came back to classical physics. Many times I told in my papers, I'm trying to recover classical physics. And let's start from the beginning, classical physics. And classical physics means ether, and I named it medium because I saturated this medium with some kind of particles. In our air we have oxygen, nitrogen, hydrogen, and all this stuff. The same story with my medium. I saturated them with some particles, yes. Simple like this. But ether, the main point, that's why don't talk about what was before. Nothing. Even space, it's only of the medium. It's not existent outside of the medium, without anything, without medium. No. It's a characteristic. Why? Because in the medium we have your changes. If you have your changes, you should do something about it. You have some parameters of this medium. As I told you, impedance parameter, it is Hubble parameter. And Hubble parameter must be measured only against microwave background radiation because it's absolute frame of reference. The space is absolute. There is no change in space. Time is absolute cosmological time. I have a little bit different because our Hubble parameter is inversely proportional to cosmological time. In physics, I measure some parameters of this medium. I found this, impedance parameter. Oh, take a look. It's going down according to tau in power -1. Okay, I can introduce cosmological time because I can describe these conditions in the medium by some parameters. That's guys, please. It's the main point of my model. Medium, the beginning of the story of everything. Talk about everything. You can start only when you have your medium. But for medium, you must have at least the first ensemble of particles. You cannot talk about each particle. Quantum physics doesn't work in this case. You must have some ensemble of particles. You can introduce the notion medium, and only after that you can introduce space, time, and gravitation, the characteristics of the medium. It's a medium characteristics only. Simple like this.
The fact that we have quite disparate ideas and sometimes we get emotional. I mean, for example,
always emotional. Sorry.
No, I'm not referring to you specifically, Vladimir. Although you have apologized for it. I was thinking of, say, David de Hilster has almost challenged. I don't know if it's Roger or Franklin. I think it's Roger, to a duel, pistols at dawn or something. Over whether it's an ether model is appropriate or whether it's a particulate model. There's sort of contradictions, and they'll sort this out and this sort of thing. We get very emotional, and we have different ideas. But maybe that's good because it's at variance with what we see in the mainstream generally, where if you had a similar forum, I think they'd be all agreeing with each other and saying, yes, this is what generally accepted and so on. And there'd be a sort of a group think at the meeting, and nobody would dare to question any aspect because, that's proven wrong and so on. So it's difficult maybe to get anywhere, but it's healthy that we're all throwing out these ideas.
All right, we're almost done here. Got less than a minute. Thank you, everybody. Roger's not talking on Saturday. I guess I'm going to try to put together some of this stuff that we've talked about here for the last couple of weeks in this issue of, and I'm going to talk a little bit about it on Saturday. So probably be hearing more about it again.
Great to show this, Okay. How good is big? It's very good talk and historical as usually. Nobody knows history of physics. This is the main point. Harry, you're absolutely right with history. Go inside 100 years, 200 years ago, and you will find all these ideas before Einstein and all the other stuff, all the other